All right, this video is going to go over an example of how to find power series solutions for second order ODEs, or ordinary differential equations. So remember, for our solutions for power series, especially for homogeneous or homogeneous equations, our solution is going to look like C1y1 plus C2 y2. And that doesn't change. What we need to be able to find is two power series type solutions that we're going to then plug into y1 and y2. And the reason I can't use some of the formulas or the procedures or methods that we've used before is I don't have constant coefficients here. I do in front of y double prime, but I don't in front of y. I have a function of x in front of y. So I'm going to say that y must be of the form of a power series, n equals 0 to infinity, some constants in the front, and then x to the power of n. So using a polynomial in order to find that approximation. And I know that it's going to be convergent for all x because I don't have any singular points. They're all ordinary points. Okay. All right, well, y prime is then going to actually start at 1. And y double prime starts at n equals 2. And we're going to have the same pattern as taking the first derivative. And I have to start at n equals 2 because I can't have x to a negative power. I need these to be polynomials. All right, well, that's what I'm going to then plug in to my differential equation. And over here, I'm going to bring the x on the inside and say that this is x to the n plus 1. All right, I need to combine these into one series. So I am going to let k be equal to n minus 2 here. When n is 2, k is then 0. And n is going to be k plus 2, so just changing my index to be k, and that means I have k equals 0 to infinity, k plus 2 times k plus 1, c to the k plus 2, x to the k. Over here, I'm going to let k be equal to n plus 1, so when n equals 0, k equals 1, and n is equal to k minus 1. So I'm going to have c to the k minus 1, x to the k equals 0. All right, well, I need these to start at the same one, so let's plug in 0. I get 2 times 1, c2, x to the 0, so 2c2 plus, and now I can combine these into one summation, one series. So I'm going to have k plus 2 times k plus 1, ck plus 2 minus ck minus 1 times x to the power of k equals 0. And in order for this series to be true, I know that C2 must be 0, so that I have a 0 coefficient over here. And then I also know that this coefficients equation must be equal to 0 as well, or ck plus 2 must be equal to ck minus 1 over these two. All right, well, I don't know what C0 is. Why my pen's not wanting to write here? Okay, there we go. C0, don't know. C1, don't know. C2. All right, C3, which if I'm finding C3, that means that K equals 1, right? Would be C0 over 3 times 2. Well, I don't know what C0 is, so that's it. Like, that's all I can find. All right, C4. So that would be that K equals 2. Well, that's going to be C1 over 4 times 3. And I don't know what C1 is, so I'm just going to have to leave that. All right, C5. So that means K equals 3. So that's going to be C2 over, it doesn't matter, C2 is 0, so C5 must be 0. All right, C6. So K equals 4. That means it's C3 over 6 times 5. And so that means it's going to be C0 over 6 times 5 times 3 times 2. Let's try to keep finding a pattern here, or finding a couple more of these coefficients. C7. So that's when K is equal to 5. That's going to be C4 over 7 times 6. Okay, so C4. So that's C1, 7 times 6 times 4 times 3. Okay, and I'm going to keep going with this pattern. It so happens that every third term ends up being 0. And then I end up having a term that's determined by C0, and then a term that's determined by C1, and so on and so forth. So let's write this out, right? So y must then be C0 x0 plus C1 x to the power of 1 plus 0 plus the number in front of C3 is C0 over 3 times 2, x to the third. The number in front of x to the fourth is this, plus 0, plus the number in front of x to the sixth. I wish it was a factorial. We're going to find it. So it's a little more complicated than that, unfortunately. Okay, the number in front of x to the seventh plus 0 plus da, 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 da. Okay. So let's go ahead and kind of bring some of these together. I'm noticing I have two different constants that I'm depending on here, right? I have this one. So I could factor out a c, and I would have x to the 0 plus x cubed over 3 times 2 plus x to the 6 over 6 times 5 times 3 times 2, plus da 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 da, right? And then I would have a c1 that I could also factor out of these terms. And what would I have? I'd have an x1 plus x to the 4th over 4 times 3 plus x to the 7th over 7 times 6 times 4 times 3. Da, 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 da. And so this just so happens that, like, this is my y1 and this is my y2, and it doesn't matter that this doesn't say c1 and c2, like they're just constants. And so this is the form that we're looking for. You can try to figure out these patterns. So like y1 ends up being something of the form like 1 over 2 times 3 times, and then it's like 3k minus 1 times 3k. And then if you notice, we're going to start at k equals 0. If you notice, then we have x to the power of 3k. And then y2 ends up being, starting at 1 over 3 times 4 times, and then we do something like 3k plus 1. And those patterns are really kind of yucky for you to kind of try to figure out, and this goes to 3k plus 1. I'm more concerned for my class that you can just kind of generate these patterns here and just realize that, like, oh, these are going to be it. This is like a nice to have if you can figure out the patterns, but they do get pretty yucky in some of these. And some of them, they're not even going to have patterns. So again, I'm just more concerned with, like, can you figure out, like, these are the ones that correlate together because of their constants, and you can write it kind of like with a couple examples of the first few terms for that solution.